Thank you for joining today. We are pleased to introduce the distinguished speakers for today's webinar, an overview of courses, tools, and lessons from the Data Sciences for Chemical Industry Graduate Certificate Program. It's held in conjunction with the honor that they've received the David Himmelblau Award for Innovations in Computer-Based Chemical Engineering Education that they received this last year. We'll have our first speaker, Dr. Andrew Medford. He's an associate professor and J. Frank Scarborough Faculty Fellow in the School of Chemical and Biomolecular Engineering at Georgia Tech. He earned his PhD in chemical engineering from Stanford University in 2015. Dr. Medford's research focuses on leveraging materials, informatics, statistics, and machine learning to enhance atomic scale simulations in surface science and catalysis. His expertise includes heterogeneous catalysis, oxide surface chemistry, densital functional theory, kinetic models, uncertainty quantification, and Bayesian optimization. Dr. Medford has been recognized with several honors, including the AIChE 35 Under 35 Award in 2020 and the ACS CATL Division Early Career Award in 2023. And then partway through, we'll turn the presentation over to Dr. Fanny Bhukalova. She's an associate professor and Glenn T. Wright Faculty Fellow in the School of Chemical and Biomolecular Engineering at Georgia Tech. She received her PhD in Chemical and Biochemical Engineering from Rutgers University in 2013. Dr. Bhukalova's research lies at the intersection of process systems engineering, mathematical programming, and advanced data analytics. Her work focuses on developing novel modeling and optimization tools for applications in energy systems, pharmaceuticals, and sustainable manufacturing. In 2022, she was honored as the inaugural recipient of the Institution of Chemical Engineers Junior Sergeant Medal for significant contributions to computer-aided product and process engineering. So with that, it's my pleasure to turn it over to this fantastic group of researchers who have earned this David Himmelblau Award for Innovations in Computer-Based Chemical Engineering Education. And welcome, and thank you. Thanks for coming to present today.
Thanks, John, for a fantastic introduction, and thanks for the invitation. It's really an honor to be here speaking on behalf of the team and to share with you all a lot of the things that we've been working on. And so the talk will kind of start off with an overview of the whole program. Then we'll go through some of the details of the two courses that Fanny and I teach, and then finally go through some more detailed lessons and sort of things that we've implemented in these courses. So the certificate program, if you're interested in signing up, the link you can go here and find all of the information. This started back in 2019, and the idea here was to have a credential that helps working professionals or graduate students in chemical engineering prepare for the new tools and emerging tools in data science and machine learning that were sort of coming onto the scene around that time. We've had a lot of companies that are affiliated with this. So we've had students from some of the big names like 3M and Dow and Intel, but also some smaller companies, the Mosaic companies, a fertilizer company, TE Connectivity. So we've had a pretty diverse set of professional students in the courses so far as well. At a glance, kind of some bullet points here. This is an online graduate level certificate designed for chemical engineers by chemical engineers to sort of get them familiar with the tool sets and the language of data science and machine learning. I'll say a bit more about the structure later on, but it's 4 total courses. 2 of them are the core courses that Fanny and I teach, and then 2 of them are electives. Our goal is for all students to learn how to handle manufacturing systems and chemical data, including some of the common challenges, and learning how to pair these analytic techniques with process optimization to make better engineering decisions. We have a lot of elective options. I'm going to talk more about this later on, but you can sort of see the list here. Some of them are things that you might expect, like going deeper into machine learning and databases, but we also have some breadth as well, things like cybersecurity and public policy. One thing that's interesting about this certificate is each course is really just as rigorous as an on-campus graduate course. These are not, something where you can just watch videos and, take a multiple choice question and get a piece of paper. These are real graduate courses. However, they're designed to be flexible, fully online, asynchronous to meet the needs of working professionals. We know that folks can't travel to campus if you have a job and a family. And we also looked at an option for fewer credit hours and lower costs than a master's degree, to have something where, people who just want to get the basics and learn a little bit more about these emerging tools can do so without a huge commitment. And so here's a visual representation of the structure. So the core courses are data analytics for chemical engineers. This is the course I teach, and data-driven systems engineering. This is the course Fanny teaches. We're going to talk a lot more about those later on. And then from there, we can leverage a lot of different elective courses. Georgia Tech has one of the largest online masters in computer science programs in the world. And so that gave us a fantastic foundation to build off of. We have a number of OMS analytics electives that folks can choose from. Some examples are listed here. These are also, fully online, asynchronous, available for professionals. And then also the OMS cybersecurity program has some electives that you can take if you're more interested in learning some of the other aspects of data and security in the chemical industry. A bit of history on the program. So this started way back in 2016, 2017, when Fanny and I both got hired around the same time. And I think that there was a recognition on campus from the research side that graduate students were having trouble getting the training they needed in data science and machine learning. And a lot of different faculty wanted to have some elective options so their students could learn these skills. Of course, there's lots of options on campus, but it was very difficult for our students to get in. These were highly competitive computer science and AIChE electives. And so basically, we had a big need from our graduate population to have more courses in this area. So Fanny and I started developing our two courses back then, just as these were undergrad, in-person, traditional kind of elective graduate courses. Around 2017, 2018, after these courses were online and being taught, David Scholl was the chair at the time, and he started talking to the Industrial Advisory Board and was getting feedback from companies that they really would like to have an option to send working professionals back to get retrained in some of these basic things that were coming out. Not something that was really as large as a master's degree or as sort of big of a commitment as a master's degree, but some way for working professionals to get familiarized with some of these emerging tools. This was kind of around the same time we started talking with Carson and Martha about how this might look. And of course, our graduate students wanted these classes as well. And so we were trying to figure out how do we satisfy the need from the graduate side, the need from the professional side, and the need from the undergraduate side. And we came up with this idea to basically do all of them at once. And so that was the idea here, was to create a program that serves all three student populations: grad, undergrad, and professionals. These are small, fewer than 50 student classes, with assignments and assessments that are exactly the same as what you would get in any graduate elective in chemical engineering at Georgia Tech. So you have homeworks, you have projects, you have exams. These are again, very sort of interactive learning experiences. The leadership was really critical in figuring this out. So there were administrative challenges that I still don't totally understand how Martha and Carson managed to make all this work, but you can imagine that kind of having courses on campus that are cross-listed across all of these was challenging, but they figured out how to make this work. We partnered with the Georgia Tech professional education team to develop the online materials. They had a lot of experience in doing this, and a lot of kind of infrastructure for that. And we launched the certificate in 2019. In our first class, we had students from 3M, Mosaic, and Dow. And this was around the same time that we got access to this the Dow data set that was provided by Leo Chung and his colleagues, which was a set of real process systems engineering data from Dow. So we integrated that into the course as well. I'll say a bit more about that when we go through the courses. And so since 2019, we've been offering the certificate program. We've had a couple of nice developments. So as of about a year ago, our courses are all now approved as analytics master's degree electives. So if you decide to transition from the DSCI program into a master's degree, all of our courses count and you've made progress. Of course, we've continued to improve our courses and try to keep things updated as we go along. And we've been very fortunate to receive some awards for this. So in 2020, we received the Campus Curriculum Innovation Award, and of course, last year, the Himmelblau Award. So we feel like we're really happy to have created this successful program. And so currently, we have 35 students enrolled. 25 different faculty members across campus advise these students, the graduate students in the program. So you can see there's a very diverse set of grad students. Overall, we have had 47 graduates, 14 of which were external professional students, and 2 of those external students proceeded on to a full master's degree in analytics. We've also had over 100 undergraduate students who have taken the courses. So this has been really popular with undergraduates. As of last year, they launched an AI minor on campus. The undergraduates don't get the certificate. So the certificate program is strictly a graduate certificate program. The undergraduates have slightly different requirements in the courses. They aren't as responsible for formulating the projects and so forth, but they're still able to participate and learn from these courses. So this has been a fun experience in seeing how popular it's been with undergrads. You can see over here on the right just some of the kind of big picture statistics for cost and timeline and so forth. And again, this is available through the website. If you're interested in this, please go do check that out. We're always interested in having more external students. I think that they bring a really nice kind of different perspective to the course. And so that's one of the things that's been cool, is to see how professionals and undergrads and grads can all work together. All right, so transitioning into some of the curriculum before we go into the core courses, I just wanted to give a high level kind of feel for what electives students take. And this is an incomplete list, but some of the popular electives that students have taken. You can see, again, some of the usual suspects, things you might expect, like computer science, big data systems, database concepts, machine learning. But you can also see some things that are a little more broad, like information security policy and statistical mechanics. So things that go into some of the more fundamental aspects and connections between chemistry and statistical learning. This is a dynamic list. So our electives, we have a committee that approves new electives, and we have the 3 criteria over here. But basically, we try to think of 3 different reasons that you would want to take an elective. One is kind of real world data, getting experience working with different kinds of real data you might encounter in engineering problems. Another one is to go deeper into the math, so foundational principles of math and statistics that underlie these methods. And then the third one is more practical, so building tools and databases and software that you can use to implement these things in practice. The 2 core courses, we're going to transition now. I'm going to talk in depth about mine. So mine is this data analytics for chemical engineers. This is more of the intro course. And then Fanny's course is data-driven systems engineering, which really shows how to apply these tools to chemical process optimization. So my course is, I would describe it as basically an overview course in data science and machine learning. You can see the outline here. We go through some general topics, numerical methods. We like to start off with just the basics, reviewing the basics of Python, linear algebra, and optimization. Our students, I'll say a bit more about this. They come from a very diverse set of backgrounds and set of skills. So we like to kind of set the tone in the beginning to establish that this is a math and programming class, and make sure that folks all have the basic background in linear algebra and programming. From there, we go through regression models, focusing on a few different algorithms, common algorithms, as well as some concepts like cross-validation and regularization that are maybe not so common in traditional statistics classes. We also talk about classification, introducing the basic kinds of classification models, and talking a lot about how to set up and evaluate classification models. From there, we kind of take an intermission around the midterm and talk about data management, and give just a very brief overview of some of the more practical things that you encounter in data science. And so how do you wrangle and clean data? How do you work with APIs that can allow you to pull data dynamically from websites? And just give a few examples from chemical data sets of the kinds of problems you might encounter when you're working with real data. From there, we go into what I call exploratory data analysis. This is basically unsupervised learning. So we cover both dimensional reduction techniques as well as clustering to try to give the students an idea of when you would use unsupervised learning techniques to kind of explore a new data set that you maybe aren't so familiar with. And then we finish up with what's formally called feature engineering, but I think would more accurately be called advanced or additional methods. So we go through some of the sort of more advanced techniques like supervised dimensional reduction, symbolic regression, feature selection, and a brief introduction to time series analysis, just to give an idea of what's different when you're working with a time series versus independent data, since there are a lot of time series data that you encounter in chemical process systems data. I think if you look at this overview of topics, it's quite similar to what you'll find in most other sort of intro to analytics courses, and that's partially by design. I think what really sets the course apart is the data sets that we use. So we use data sets that are familiar to chemical engineers. Spectroscopy, we have some IR spectra data that we pull from NIST, and we use that to illustrate things, problems in regression and curve fitting. Chemical process data. So this one is that Dow data set that I mentioned earlier is I think a really important part of the course, because this is chemical engineering, right? This is a chemical separations process, and you have an impurity, and the impurity depends on the operating variables that are in the spreadsheet, and you have to try to figure out how things are correlated, and build models to correlate between these. And this is a real data set that was graciously provided by Dow. And I think this has been very inspiring for the students, particularly the undergrad and the graduate students, because they know that this is real industry data. And so it gives the course kind of a feeling of being grounded in industry problems. And then we have another data set that's an example of material synthesis data from the literature, where folks had used some models to try to predict whether or not perovskites are stable. And so this is, again, kind of a problem that a lot of chemists might face in trying to synthesize new materials. I'd say the biggest challenge that I've faced is diversity in prior experience when students come into this course. So when we started, we knew this was going to be a problem, but we thought it was going to be a problem for the obvious reason. We thought, well, we're putting in undergrads and professionals and grads all in the same course. We're going to have a huge variety of skills. And we do have a huge variety, but it's actually across the classes. And so, you can have anything from an undergrad who only has one programming course to undergrads who are seniors that are double majoring in computer science and already know Python, as well as I do. Same thing with grad students. Some of them are experimentalists and they barely ever write any code. Others are students in my group who are writing Python code and doing machine learning models on a day-to-day basis. Industry is no different. Sometimes we get students who haven't taken a programming class since Fortran was the standard, and really, need to get refreshed on programming. Other times we have industry professionals who are actively working in data science roles at their companies. So our strategy here has been to keep the course inclusive. We think that really the key thing is this course is supposed to be for people who have little to no prior experience in these methods. It's great that people who do have experience want to take the course, but we want to make sure that we don't create something that's not accessible to folks who are trying to learn this stuff. We encourage the students to work together. So Fanny will talk more about the groups, the project groups, but we have surveys and we try to nucleate groups that have at least a couple of students who have prior programming experience, and we encourage the students to learn from each other. Another technique that I've used in the course is to combine auto grading and peer grading on the homeworks. So the first part of the homework is all auto-graded. You can submit as many times as you want, and you can kind of keep trying things over and over again until you figure out all the syntax errors and get over the sort of programming hump. And then the latter half is open-ended questions where you then apply those skills to problems that don't really have a clear right answer. And then we use peer grading for that. So the students can look at other students' answers, and that gives a great way for them to see different ways of approaching the problem, different ways of writing code. It makes it so that they're not just seeing, my particular coding style or my TA's coding style every time they look at the solutions. And then finally, the course project is really a foundational aspect of both of the two courses. Fanny is going to speak more about that, but I think this has been a great way to keep those really strong students engaged, because they can bring in their own data sets and they can challenge themselves and find ways to make the course interesting, even though they may already have those basic skills. All right, and so in the end, I think that we usually do some informal surveys. This is from a couple of years ago, but it's pretty much consistent every time I do it. Asking questions about kind of how difficult the course was and whether or not it was useful, with a particular emphasis on how it is for students who didn't know Python coming in, because that is, again, one of our really important demographics, students who maybe they might know MATLAB, they might know Fortran, but they've never used Python before. And so on the left here, you can see most students have little to no familiarity with Python when they come in, but the programming difficulty of the course, they find it to be sort of average overall. So I think this is a good sign that, even the students who come in with little experience are not totally overwhelmed by the programming. If we look at the overall difficulty of the course, the students actually find that it's pretty difficult, so about a 4 out of 5 for most students. And interestingly, they find that the overall difficulty is more challenging than the programming. So to me, this is a good sign. It tells me that the programming is not getting in the way of learning the concepts here. And then the most important one I ask is, was it useful? So it was difficult, but was it worth it in the end? And you can see that overwhelmingly students do find the course useful. And this is regardless of what their experience was coming in. So I think this is a really encouraging kind of sign that this course is a good on-ramp for students from a wide range of backgrounds. And you can see some student quotes here. I'm not going to read them to you, but overall, at least anecdotally, we feel like the course is a good balance between kind of new concepts that are accessible and things that challenge students who have more background. So with that, I'm going to turn it over to Fanny, who's going to talk about her course and finish out the rest of the presentation. So I'm going to stop sharing here.
Great. Thanks, AJ. Just a second to transition. Great. You can see my slides.
Yes, I can see it.
Great. So this
You're not in presentation, Fanny.
Sorry. Oh, sorry. Is it in presentation mode now?
Not yet. Sometimes you have to switch which screen is sharing. Yeah, multiple screens.
Yep, I just sorry about that.
No problem. And just for those that, if you have questions along the way, let's go and put them in the chat window, or you're welcome to, at the end, we'll unmute microphones and have a discussion, Q&A part of the presentation.
Is it good now?
Yeah, looks good.
Good.
So yes, transitioning to my course, which I feel I need to motivate a bit more because it has a unique structure in terms of the course has 2 parts. The first part, we really just forget about the data-driven piece. Overall, the course is focused on decision-making using data. But we start the first 4 to 5 weeks on just the basics of optimization. So how do I formulate an optimization problem, go from a conceptual description of a decision I have to make in an engineering setting? How do I define variables, constraints, my objective? Does the problem have to be linear or nonlinear? Is it convex, non-convex? And then once I know what it looks like, what tools do I have to solve it? What are the optimization solvers available? A little bit of the theory that goes behind those solvers in a linear, nonlinear, mixed integer scenarios. And how do I interpret the results? Did I use the right tool to get a local optimum or a global, and what's the difference? And we do that also in Python, and we do use the Python-based environment for optimization developed at Sandia National Labs, Pyoma. So we do have a tutorial at the beginning of the course on that. And once that is finished, we transition into the data-driven part of the class, which is most of the weeks. So now we transition from, okay, well, the first part showed you how you can write equations, and what optimization problems look like. But what happens when your starting point is not equations. What happens when you're just given a data set, but your end goal is to make a decision, learn something from that data set and make a decision. What happens if your problem relies on a simulation that's kind of like a black box, is so expensive that you can only use it to generate data. And we talk about how to design design experiments, computational, or whether the data came from experimental techniques, how to merge the equation-based part of the course with the data-driven part of the course to have sort of overall hybrid models that we optimize, different types of data-driven optimization strategies with surrogate models or machine learning models embedded or just with data. And there's 2 weeks where we also talk about, well, you know, if the data can't be pretty or designed, it's real engineering data with, you know, dependencies and correlations that are known and missing data and all those things. How do we pre-process it to get it to a point where we can do all that optimization? So, you know, obviously, for those of you who might know me, part of the reason this course started this way is because that sort of defines the research that I do. But I think there's many reasons why when we try to design a chemical engineering program for data science, data-driven decision-making, integrating optimization is particularly useful, because a lot of times in an engineering setting, we don't just want to learn something from data, we want to use what we learn from it to make a decision, solve a design problem, solve an inverse problem. And then once the material was designed, I found that there's a lot of here are some examples where, you know, connections to optimization, connections to the first 5 weeks of the class where I push them to struggle through some theory and math that sometimes they don't particularly like. But then when we go back to talking about how to train or tune a machine learning model, we can make links to, okay, well, what solver do we use here? It is an optimization problem. Did we find how many local solutions are there? And when we talk about regularization, again, there's opportunities to talk about the objective function, and the different penalization of your objectives and how is there a convex formulation or not. When we talk about physics-informed machine learning, again, there's connections to Lagrange functions and, how we add those terms in the objective. When we have a module on support vector machines and regression, which is a popular machine learning tool for classification and regression, again, there's opportunity to go back and talk about, how people actually formulated this to begin with slack variables, and how people have actually figured out a way to use to solve the problem in dual space and actually make a convex problem out of something that in the primal space would be originally very difficult to solve. So when they see those connections with theory and how, modern machine learning tools that people use were based on, then the theory behind it was based on a lot of, optimization theory, I think it all makes sense. And obviously, when we talk about some more fancy machine learning models like neural networks or Gaussian process models, we really don't stop at, okay, how did you tune it? But then we look at what the actual equation looks like. And if you're trying to optimize something with an embedded machine learning model, what does it look like? Is it convex? How difficult is it to optimize that? And, what solver should you use? So lots of connections. And here are some in AJ's course, the course is a combination of lecture material and Jupyter notebooks. Students can code their own solvers or have done that in their projects. We talk about, different types of surrogates, what they look like, and what, we always link the machine learning piece with how does that affect the final decision that we make when we use that model in our optimization. And in terms of the quotes, the feedback we get from students, There's a lot of positives. Students find that there's a good balance between theory, application, and computational skills. They find that the theory they learned was relevant, especially when, again, we link it to how it relates to why these methods are so efficient. And they like the Jupyter Notebook aspect of things. Of course, there are some more concerns. Some students who come in with a very little programming experience or very little optimization experience find that it's a lot of material, and I agree with that. And it could be potentially broken into 2 classes. It could be potentially broken into multiple classes. But overall, I think taking that feedback into account has led me to really, talk about expectations and what this course is about and what this course requires at the beginning of the class, so that students are aware what they're signing up for. But it really does make sense to have those 2 together in a single semester. And then if someone wants to learn more about the foundational math behind the different optimization methods, as you saw earlier by AJ's presentation, they can take more specialized courses on that. Other examples, as I said, I mentioned these already. There's connections with physics for machine learning and Lagrange functions, support vector machines, and duality. And even looking at how principal component analysis is formulated as an optimization problem. So the optimization part of the course also is something that students really like. They find that it helps them set them apart when they're looking for jobs. And one of my most favorite quotes, I see optimization problems everywhere now. And I think one of the things you'll notice is that there's some overlap with what AJ teaches in his course and in my course. And we've had potential concerns about that, but overwhelmingly talking to students, the fact that the 2 courses discuss some similar things, but from a very different perspective, they really like, because it really helps them understand where it can be applied, what's the method behind it, when to use it, when not to use it. And again, in my course, we have the semester-long project. The difference is that the project can't be just a learning component. It has to have a data component and an optimization component. And we are here as a list of where some students find examples, case studies, data sets to use, and examples of some of the projects from, optimizing concrete formulations to bioprocess operation to metamaterials and heat pumps. And this is just a small list. Now, transitioning more to teaching innovation components in our classes that we've worked on and they have worked really well for us based on student feedback. These are listed here, and I'll go into each of them a little bit more in depth. So AJ mentioned this already, but because of this unique composition of our classes, where we have professionals, grad students, and undergraduate students in our class, we do everything in vertically integrated teams where students from each of those groups work together in a single group to solve the projects. Strong focus on, process engineering data sets. Sometimes, example where we have worked with a company to create a case study, or students actually who are professionals bring in problems from their job to solve throughout the semester. The flexibility of the asynchronous format is actually something that obviously is important to our professionals students who are not in Atlanta, but even residential students, graduate students and undergrads actually like this format. It gives them more flexibility. And we'll talk a little bit about the structure of our assessments. We have many different types of check-ins, assessments, from weekly knowledge checks to homeworks and exams that are all coding-based. And we'll discuss a little bit the tools that help us do that very nicely. So working with vertically integrated teams has been a really nice to see the impact of it. So teams are assigned to have a diversified skill set. And as AJ said, at least one member has a data set. Teams define their own projects, but it's very clearly communicated that the professionals or graduate students, the graduate members of the team are responsible for creating the case study or bringing in the data. Teams are required, and it's part of their grade, to assess each other, to meet weekly to discuss the project, and they can also discuss homeworks and assignments. And we have different types of assessments to ensure participation. And this diversified, vertically integrated structure has helped, I think, contributed towards having really different examples of projects across chemistry and chemical engineering, from optimization of chemical processes to molecular material property-based projects, to biochemical reaction networks, and several that actually deal with real experimental data that, you know, grad student collected in their lab. So overall, this structure seems to work really well. We get a lot of good feedback from students that enjoy interacting with peers from different groups, and apply what they learn in class in real data sets. Where do the data sets come from? A little bit more on this. First of all, when we designed the program, we thought that this is a particularly important part to get right, because part of the other reason we found there's a need for these classes is a lot of our students may have signed up to take you know, computer science-led courses, and the types of case studies, data they use, they can't relate to as much, or the skills or the methods that are used to solve those problems might not be that relevant to the chemical process industry. So we wanted to structure our courses around this. And we have found that students really like that aspect of the class. Some more examples of data sets, and you see figures here provided by AJ. The infrared spectroscopy data set that he already mentioned, the Dow data set that we've mentioned several times, or the material synthesis data set. And where do they find these? In addition to resources I already talked about in my course, their own research data, chemical databases, machine learning databases, publications in the literature. Several groups have actually found a paper that has released all their data, and they basically reproduce that paper through their project and learn a lot through that process. And some examples from general databases like Kaggle, although we do find that a lot of the data sets on there that are not engineering based actually don't work as well in our setting. And the good news is that data is increasingly easy to find due to recent trends in publishing and sort of doing things more open source and with much more transparency. The flexible online format shown here, so the way the course is structured is, you know, every week there's a module that unlocks, releases a set of videos that students watch. The videos took a long time to make. AJ and I can tell you more about this, but we work with professionals from our professional education program who really helped us make really nice slides, ideal for this kind of setting, broken down into 10-minute videos by topic. And so each week, the students get the list of modules to watch. And each week, they have a sort of simple knowledge check type question on Canvas to answer based on the material that they watch. Assignments, there's many different assignments, and a lot of them, due to the nature of the material, are coding based. So we have weekly or bi-weekly homeworks and exams. A tool that we have found to be extremely useful is Vocarium. It's a tool that integrates well with Canvas, and it allows us to create homework and assignments that are Jupyter Notebook based. One thing that AJ already mentioned, our homework sets combine auto-grading parts and more open-ended type problem-based parts that are peer-reviewed. Vocarium is a really nice environment if you haven't used it, because it allows you to also pre-install a lot of solvers that you're going to need and avoid having a ton of installation issues, especially during exams. And so students really like the auto-graded sections. It gives you the opportunity to really get instant feedback. And surprisingly, they also like the peer grading. It's not a significant time commitment for them to grade 3 anonymously assigned projects, and overall it really helps them learn more by looking at other people's solutions. So if you want to know more about all of these things, we have published a paper in Chemical Engineering Education where we have more information about the data sets, the resources, and student feedback. But getting to the most important part, the impact this has had. And we have more stories, but here are just 3 that we'd like to highlight with their permission. Rahul was one of our PhD students that took the certificate. He used what he learned in the courses during his internship at Dow. Actually getting the internship also helped to show that he had this background, and then decided to join the Dow Data Analytics group after graduation. And we have several other examples where this has been impactful in the career trajectory of our grad students. Lisa Reisenhauer is a Dow engineer. She's one of our professional students that came in without programming experience while working at Dow. She took the certificate, used this to actually build up her familiarity with programming and data science concepts, and then decided to actually enroll in the online Master's Analytics, which she's currently continuing to pursue. And based on feedback she has given us, this has really been really useful for her day-to-day job. And Zach Cooper from Mosaic Company, who came in with another colleague, actually used data and a case study from his job as the project. And through what he did in both of our courses, in AJ's course and in my course, and based on his feedback, the results that he applied during our class on that project led to an estimated gross return for his company of about 8 million. The material for our courses, we have openly shared on GitHub, and here are the links. We can provide more information. We have examples of impact on this front as well. Colleagues who have used AJ's course directly to create a course in their institution, the University of Virginia. And students use the material after graduation. We have evidence of that. And we're currently considering to actually reformat the materials and make them into Jupyter book format that would be easier to access and reference. Some of the resources that we recommend, we have used in our class and in our classes, and we also recommend for students to access, are shown here. From a numerical Python, so how to transition. Actually, this is a really good resource for students who are familiar with MATLAB and want to learn Python. The Pyomo, John Kitchen's a resource here, several optimization resources, books, where we take, at least I have taken resources from to create the content, and some references here. Of course, we're not the first ones to introduce or teach machine learning to chemical engineers, and so all of these resources, publications, information, training we received in the past has really helped us in getting here. Okay. So to summarize, most important lessons so far. We're really glad to see that the program has had true impact in students' research and careers. We have examples of actually these courses actually circling back and catalyzing research collaborations. AJ and I both have examples of that. We learned through this, and as you saw from the timeline, this started in 2016, that it's important to have a large team, from the inception to administrative support to promoting this to creation to giving us time to create the material to working with professionals in how to do online asynchronous format type of teaching, and of course to maintain and continuously improve the material. We also learned that there's great tools for instruction, assessment, and collaborative work in coding-based courses. And online teaching provides this opportunity to create this new structure of, for example, vertically integrated teams, which wouldn't be possible if we didn't have this online asynchronous format, bringing in our professionals with our students. Engineering data sets are critical and they're needed. And good news is that we're seeing that publishing trends are helping us with this. And the other thing we found is that, there's a lot of material online, which is great. But several students find that the structured content with frequent assessments, with one-on-one interaction with us throughout the semester and their peers, and this feedback helps them stay the course and learn how to use the tools in their own work. We have a lot of current and future plans. We're currently considering adding new elective courses, and I'll show you an example of that. We would like to every now and then update course material, and we didn't really talk about this, but the topics we discussed were, some of them are new and were incorporated throughout the years of offering the material. Of course, we want to learn from other great initiatives, and because we know other institutions are also doing this and creating material and incorporating or suggesting to our students what resources they can also use. We have a lot of thoughts. I don't want to get into it about healthy incorporation of things like ChatGPT and how it's affecting learning and assessment. We are currently working on curating a list of data sets that people have used in our classes or we have found particularly useful for teaching to publish and consolidate our resources in online books. This is an example of a course that just was offered this spring in our department by our colleague Vida Jamali. That is now an elective for the data science certificate. Vida's course is doing more in AI, so more into more fancy and cutting edge artificial intelligence methods, and also incorporation of how to do that with diverse experimental data. So it goes beyond what we discuss in our classes. She has examples for microscopy, spectroscopy, and electrochemistry. And of course, to wrap up, lots of people to acknowledge. Obviously, AJ and I wouldn't be able to create this if we hadn't received the training over the years and have all of our mentors, too many to list here. The school, NSF support, of course, CAST for this recognition, and AIChE. Our colleagues, our current chair, and Leo Chang and Chris Jacobs from Dow and 3M, respectively, who have really given us a lot of useful feedback and also sent us students. Nick Sachinidis and Jacqueline for Snedecare for nominating us for awards. That takes a lot of time. And our Georgia Tech professional education staff listed here. And actually students who have helped us with creating and curating content for these classes, which has been extremely valuable. So with that, I'll finish, and thank you for listening.
Well, thank you, Fanny, and also, Andrew, thank you so much for your great work with this presentation, also for developing these courses and making it available to industry and to academics. I just wanted to share some of the results of a participant poll. How much machine learning and data science experience do you have? And it looks like most of the participants here on the webinar are moderate or beginner, rarely use it just starting or use occasionally. And then, the question, where did you learn data science and ML? Online courses is the most popular one. Then university courses and self-taught are equally responded to. Where would you like to learn more data science ML? Online courses is by far the biggest one. And so this is a great plug for what they're doing, making this available online. Degree programs, self-teaching, is much lower on that list. And then another question, how do you use generative AI? How much do you use generative AI to help with coding? And nobody responded a high amount. It's moderate or a little just starting. A lot of times it helps you maybe create that first version of the script that you need, and then you really have to get in there, debug, and really customize it for your application. So I think that's consistent with a lot of what we've heard about generative AI, is it isn't going to take your job. It's going to basically help you be more effective. And I think that's reflected in that one. What's your preferred programming environment? I put Julia, MATLAB, Python, or other. And Python was 86%, MATLAB 14%. So it looks like, for AI and machine learning, a lot of you have responded that you're using Python. Okay, well, great. Let's jump into a few questions. We have about 5 minutes for some questions. I'm glad you ended with that slide to just mention the team that was involved in creating this. I'll just mention that Martha Grover, Carson Meredith, and David Scholl were all involved and received equally this Himmelblau Award. And can you just say a little bit about that? You started this program in 2019. When did it really start? Like, when did you guys start planning it? How long did it really take to get off the ground?
Yeah,
AJ,
I'll take this one and give Fanny a break from talking. So yeah, I would say, we started our elective courses without any broader vision of anything like a certificate program. And I can't actually remember when David Scholl, I think, was the one who first floated the idea to me, probably 2018 or so, late 2017, early 2018. And kind of came in with this broader vision of creating the certificate and leveraging our classes and taking them online. And I said, yeah, sounds great. But it certainly wouldn't have happened without that. And then, Carson and Martha, the administrative challenges, right? Of how do you have a course that's listed across professional ed and grad and undergrad, and there's a different tuition model for grads and professional ed. And so there's a lot of these things that had to be worked out that were above my pay grade, frankly. So I was happy to have the support of the leadership team in pulling that all together. But I would say from first inception to launch, probably about 1.5 to 2 years would be my guess.
yeah. And I think it really helped that at Georgia Tech already had this certificate model in place, and a great professional education group that really partners with a lot of different departments to do this. So if that wasn't in place, it probably would have taken longer.
Okay, so leveraging some of that experience, and yeah, we certainly see a lot of courses. I have so many professionals that ask me like, "Hey, would this be a good idea to boost my career to go through this Georgia Tech program?" And I always tell them, "Yes, I've heard such good things about it." So, well, that's great. Okay, let's open it up for some questions from the audience. If you have questions, you can either put that in the chat window or you can unmute your microphone as well. Okay, I have another question here. What is the preparation for the program to come in for somebody who has very little programming experience?
I would say it depends on your tolerance for pain to some extent. So you can come in with nothing would be my short answer, but it's going to be a really steep learning curve. What's best if you have absolutely zero programming experience, we strongly recommend Georgia Tech actually offers a 2-week Python boot camp. There's a ton of other kind of Python boot camps out there, but I think those kinds of things are really helpful just so that you know how to write basic code and you know how to run Python on your environment, and you have some familiarity with it. But we have definitely had students who have come in, our undergrads, they take one MATLAB course and I don't think they pay very much attention in it, to be honest. And so then they come in and they're kind of starting from almost zero, and they find it difficult, to be clear, but in the end, they're usually able to get to a point that they feel like they can do things. We usually recommend taking my class first if you have little to no experience. I think it would be even more difficult to jump into funnies.
Yeah, exactly. Yeah, and I think communicating this clearly is a key. And I always tell students that, if you have little experience but a lot of motivation, you may need to put in a bit more work than others who come in with more. But because these are electives for a lot of our students and they're doing it because they really think this is useful and important and it will help their careers and everything, I find that they, even if they struggle more, they do see the benefit, and it's worked out actually, even with people that came in with little experience.
Great. We have a couple questions here in the chat window. First of all, how much does it cost to earn the certificate?
It's a great question. I think the last number I saw was $1,100 per credit hour. So each course is 3 hours, 12 credit hours. So, about 13,000 total to get the entire certificate. I would note you don't have to do all of the courses. So we would love for you to get the certificate, but if you just want to take one of these courses, then there's nothing stopping you from just signing up and taking them kind of a la carte. You can kind of decide how much there is, but it's sort of cheaper than a master's degree, was the goal.
Fantastic. Another question. One pillar of process systems engineering is process control. Do you have plans to include process control as a module in the data-driven PSE course?
Yeah, that it's not currently covered, for sure. Would it be, we do have an undergraduate control class, of course. Would it be something that if we had the right person, we would be interested to develop? For sure, but is not in the immediate plans. Thankfully, you have a ton of great resources as well, John.
Great. Yeah, thank you. Thanks for that question. Thank you for that answer. Now, another question here. What about scaling up to 10,000 students? What are some of the obstacles to going much bigger?
I don't want to do it, to be really clear. So we've almost intentionally designed these courses not to scale. So you could try, right, if you wanted to get an army of TAs to run the projects, but we want these to feel like real graduate courses, keep them small, keep them under 50 students. It would be really, really difficult to do the projects, even when we get to 50. Like it's a stretch to find the time to give good feedback on all of these projects, and we want that instructor contact, right? The students, they can meet with us on a weekly basis at our office hours, and that was one of the things we said coming in, is we want this to be a small, typical graduate student experience. It just so happens to be online.
Yeah, fully agree. Nothing to add.
Okay, fantastic. Could you delve into the projects just a little bit more? You have industry participants, but also you have some undergrads or graduate students who are participants who are Georgia Tech students. Can you say a little bit about how you do the pairing and just the process of somebody from industry, if they have an idea? How does that work logistically? Sometimes the company doesn't want to share data or things like that. How do you set that up so that somebody from industry brings the experience, brings the data, but then ends up working maybe with a team of undergraduate or graduate students?
Yeah. So we've had many different examples. We have had a case where, the data was from the company was a bit more proprietary, and multiple people from that company took the certificate at the same time and they made their own group. So if there's issues like that, that was just one case. It is possible to do. Obviously, they did present the results, and we have peer evaluation of projects in the end, so students can learn from that project, but not directly handle the data. We have had examples where actually people bring in data from industry that are not proprietary, and they don't have an issue with sharing it with the team of grads and undergrads and actually getting the chance to work with real data. And there's some sort of discussion at the beginning on, obviously how to, that the data can only be used for the class. I think that's in terms of handling it, how we pair students. AJ can talk a bit more, but often we do little surveys at the beginning to get a sense of what is your experience in XYZ. We also, at least I in my class, also allow students, if they have a research problem and they're taking it with a lab mate, and they can actually self-group to a certain extent if it really makes sense. And then we even have examples of people actually doing a project and then publishing a paper based on that project as well.
Okay. Yeah, the logistical side can be challenging. So that's evolved for me. I'm getting better and better at it, but I do a survey where I ask like how, Python experience, do you have a data set, all those kinds of things. And then I've recently started doing scheduling polls as well. And I have little scripts that I run to try to maximize the chance that students have overlap in their schedules, because that was a challenge actually early on. At least in my course, I tell them you should treat your weekly group meeting like it's class lecture. Like you should all be there every week. And then of course students say, well, I'm not, we can't find availability. So now I try to head that off in the beginning, and that's helped a lot.
Okay, well, fantastic. I think we're out of time now, but thank you everybody for joining. And also special thanks to AJ and Fanny for the excellent presentation, for the development, the years of development you put into this, the extra work, just a huge resource for the community. And I can see why the Computing Systems Technology Division of AIChE awarded you with this award to really move this important topic forward. So thank you again. Thanks for the presentation, and really appreciate everybody joining for the questions too.
Thank you, John, for organizing this.